Give Qwen 1.57b and Qwen 2.7b the same set of hard math problems. In Qwen's technical report, the older model scores 20.3 on the math benchmark, and the newer model scores 44.2. Both are labeled 7b. What changed inside the recipe? Qwen2 is a family of 5 text models. 4 are dense models, which use the same full set of parts for each small piece of text. 1 is a mixture of experts, which keeps many expert parts and chooses a smaller group each time. The family runs from 0.5b to 72b. A score like 44.2 sits at the end of a chain. The model has a way to spend its work, learns from chosen examples, practices giving better answers, and gets extra help with very long text. We will follow that chain, then check where the reported results improved and where they did not. We begin with how Qwen2 spends its work. Start with one piece of text moving into the model. Qwen2 uses the same tokenizer as earlier Qwen models, the tool that cuts text into small pieces. It also keeps the same basic decoder-only shape, which reads the pieces so far and predicts the next one. Most of the machine stays familiar, while the way it shares and chooses work changes inside. Inside Qwen 272b, 64 small attention workers, called query heads, look for useful earlier text. 8 key and value heads hold the lookup information. Each one serves a group of 8 query heads. This sharing pattern is called grouped query attention, and it reduces the key and value information stored for each text piece. Now send one text piece into Qwen 257b, A14b. The model contains 57 billion parameters, the learned numbers inside it. For this piece, only 14 billion parameters are active. A gate chooses which expert blocks handle the piece, so the model can keep many parts without using all of them every time. These two changes spend the model's budget in different ways. Grouped query attention lets many query heads reuse key and value memory. The mixture of experts chooses a smaller active path through a larger set of parameters. The shared rule is to reuse a stored lookup across several heads and activate only the experts chosen for this text piece. A machine that shares and selects work can still learn from poor examples. The next stage is its training material. Picture every training token as one tiny card. A token is a small piece of text that the model learns to predict. Qwen 1.5 used 3 trillion of them. For Qwen2, the main pile grew to more than 7 trillion. The team changed what went into the pile too. Compared with Qwen 1.5, Qwen2 had more code, mathematics, and material from many languages. The team used stricter filters to reject material it judged low quality. Then the team loosened the filter, which produced a still larger pile of 12 trillion tokens. The report says a model trained on this pile did not improve significantly over one trained on 7 trillion tokens. In this experiment, the larger pile did not produce a clear gain. The team therefore used the more strictly filtered 7 trillion token corpus for Qwen 2 1.5b, Qwen 2.7b, and Qwen 2.72b. The report does not tell us which model ran the 7T versus 12T test, what scores it got, or how much training work each run received. Pre-training on these chosen tokens teaches Qwen2 to keep predicting the next piece of text. The team then gave it a more focused lesson in following instructions and producing useful answers. That is the next stage in the chain. Take one simple instruction. Write exactly 5 words. One answer says, "Wear the blue hat today." A model can generate a small Python check that counts the words and marks this answer as a pass. Qwen2 used generated checks like this for explicit rules, such as length limits. Math and code can use checkable results too. For mathematics, a correct final answer passes one gate, while a model also judges whether the reasoning looks reasonable. For code, the answer can be compiled and run against tests. These checked examples joined examples chosen by people in a supervised fine-tuning set of more than 500,000 examples. Supervised fine-tuning means showing the model a satisfactory answer for an instruction, then adjusting it to make answers like that more likely. This stage gave Qwen2 a focused lesson in how to respond. Qwen then learned from answer pairs. For one instruction, one answer is marked preferred and another rejected. The offline stage starts with a fixed collection of these pairs. This is called Direct Preference Optimization, or DPO. It adjusts the model so preferred answers become more likely than rejected ones. The online stage creates new pairs as learning continues. The current model writes several answers. A reward models then score those answers, pick the most preferred and the least preferred. DPO learns from these fresh pair, the model writes again, and the cycle repeats. The updated model then moves to a different test, reading text far longer than the length used in training. The strip ends at 32,768 tokens. Qwen2 reached that pre-training length only in its final phase, after starting at 4,096. But the exam strip keeps unrolling to 256K tokens, 8 times as long. Qwen2 72B Instruct must now work far beyond the length used in pre-training. Qwen2 uses 2 helpers for this longer range, yarn and dual chunk attention. The report tests both helpers together and does not measure their effects separately. Needlebench hides 2 to 5 facts inside a long passage, then asks the model to find and combine them. At 256K tokens, Qwen2 72B Instruct has a reported score of 17.13 without the 2 helpers. With yarn and dual chunk attention, the same model scores 85.21. LV Eval combines 11 question answering datasets where the model must use several pieces of evidence. At 256K, Qwen2 72B Instruct has a reported score of 2.88 without the helpers and 42.35 with both. The report checks whether key answer words appear, a looser rule than LV Eval's original strict score. These before and after scores show useful length extrapolation on 2 tests. Length extrapolation means working beyond the length used in training. To see how Qwen2 reaches past 32K, we take the 2 helpers one at a time, starting with yarn. Imagine the model uses several rulers to mark position. One has fine marks that change quickly from token to token. Another changes slowly across a much longer span. Stretch every ruler by the same amount, and the fine marks spread out too, making nearby positions harder to tell apart. Yarn gives each ruler a different stretch. The fine ruler stays nearly the same, the broad ruler stretches much farther, and a middle ruler lands between them. Nearby tokens keep the fine changes that separate them, while the broad ruler can cover the longer strip. Changing the rulers can also spread attention too evenly. Attention is the strength of the model's look back at each earlier token. Yarn sharpens those strengths, so the strongest links stand out again without removing the others. Yarn changes the position rulers. Dual chunk attention. The next helper changes how familiar distances are reused across chunks. Use a tiny example. There are 12 tokens, but suppose the model learned position distances only from 0 to 7. The last token is 11 steps from the first, a distance it has never seen. DCA splits the line into 3 chunks of 4 and reuses positions 0 through 3 inside each chunk. Inside one chunk, DCA keeps the exact nearby distances. In the final chunk, the last token is 3 steps from the first, just as it was before the split. But local links alone would hide the first 2 chunks, including any fact stored there. DCA keeps those older tokens available with a second kind of link. It gives older chunks a coarse distance from the familiar range instead of their exact distance. The model can still look back at their content, but it no longer knows exactly how many whole chunks away they are. One problem remains at a chunk boundary. The first token in a new chunk sits right beside the last token in the previous chunk, but the coarse rule can make them look farther apart. DCA gives the previous chunk its own bridge, so those 2 neighbors look 1 step apart again. DCA now keeps every earlier token available, while every position distance stays inside a familiar range. The Qwen2 report does not give its exact chunk settings. The completed DCA result joins yarn, and both return to the larger Qwen2 package for the takeaway. The scorecards from the beginning are back. On the math benchmark, Qwen 1.57b scored 20.3 and Qwen 2.7b scored 44.2. We can now place that jump at the end of the whole Qwen2 recipe. That recipe has 4 parts. Qwen2 spends its work more selectively, learns from better filtered and more targeted data, practices with answers that can often be checked, and uses extra methods to read beyond the length it practiced on. That was Qwen2, a model family improved in how it works, how it learns, and how much text it can read.